So I want you to, instead of it saying permutation involving grouping, I'm going to say let's get rid of that, the grouping, and you'll see later, end of the unit. Some students mix this grouping up with another type of grouping. So how about we just get rid of that and just say involving staying together or items or people being beside each other. Let's talk about it in those terms. Staying together, beside each other, an artist wishes to, and so let's talk about these cases, okay? So an artist wishes to display her 8 paintings at an art gallery. How many ways can she arrange the paintings? How many can we pick at a time? Like how many, do we have to choose only 5 like earlier? If it just says 8 paintings and you want to arrange them, you actually have 8 available. So it's 8, 7, 6, 5, 4, 3, 2, 1. I'm not going to do the answer to that one just yet. How else can you write this if you have a number and it goes down all the way to 1? 8 factorial, right? It's the same thing. Just a lot faster, in my opinion. How else can we write this using permutation notation? From the 8, we pick 8, right? 8 pick 8. What is this? 40,320? I don't know if you have your cheat sheet. Did I ask you to write down the, like on page 13, 8 factorial is 40,320. It's just, it makes it a lot easier. 40,320 for all of them. Arrangements or ways or something, ways to arrange. So this is the same as taking pictures. Because when you move one, as soon as you move it around, it's a different arrangement technically. Okay. What about this? If an artist wishes to keep her 3 favorite paintings together, keep her 3 favorite paintings together, beside each other, how many arrangements are possible in that case? This is a classic. Okay. So the way I like to do, I'm going to actually ask you to draw out your 8 again. So 3, 6, 7, 8. And imagine somewhere in these 8 there are the 3 that you always want to keep together, okay? So I kind of imagine at first they are right here. Even though it wouldn't matter which 3 you group up, but just do that, right? So I'm going to say, let's pretend like these are the 3 paintings you want to keep together. Keep together. Okay. So they, as long as they're beside each other, everything is good. Okay. So let's zoom into this little circle here. How many ways can you arrange those pictures? Wouldn't you say it's just 3 times 2 times 1? Like you can actually move them and make different pictures, the different arrangements by just moving them inside of the 3. As long as they're beside each other, that is fine. We call that 3 factorial, right? 3 factorial. Okay, that bag, that circle is all of them together. Now we're going to zoom out. These 3 can be moved across, right? You can have these 3 and then these 3, like you can shift that all across and everything else goes all over the place, okay? But these 3 need to be kept together. So when you zoom out, I'm going to use a marker for that. I consider this as one slot, this as one slot, this as one slot, and so forth. So I know this looks like a longer slot, but I'm treating it as one that I can move around, and I can move this one over to this side, this one over to the other side, so I can move them as long as I keep them together. So when you zoom out, okay, how many different objects do you have if you zoom out? Count this one as one. 1, 2, 3, 4, 5, 6. You've got 6 items that you can move around for your arrangement. So that's the 6 factorial part outside. I call this zoom out. You zoom in, I will call this zoom in. Zoom into that group that needs to stay together. You can change those around, but you can also zoom out and change everything else that remains around as well. So your answer here is 3 factorial times 6 factorial. That's how things being kept together works. Okay, so let's do the math here. So you're having factorial. Grab your calculator. 3 factorial is what? 6? 6 factorial? Cheat sheet? Is it 720? I think it's 720. So 4,320 ways. How many did we have earlier when we didn't have restrictions? There's 40,000 arrangements you can make. As soon as you keep, in this case, 3 of them together, you're down to only 4,320 ways of arranging it. Because these must be kept together. Let me do this here. Let's grab some scrap paper. See if this is going to help you out. I'm not going to do all 4,000 of them, okay? There's 4,000, but let's assume this is the first one. So let's assume these stay together here, right? And then I'm going to do the 8 again. 3, 6, 7, sorry, 8, it's supposed to be 8. So let's say I move these over, right? I move them over here, bring this one over to this side. That's another arrangement, okay? 1, 2, 3, 4, 5, 6, 7, 8. So now I can shift these over one more, right? And so this whole group can be moved around. So I treat that as almost like one single block that I can move around. And that's why I have 6 factorial. I count this big group as 1. So 1, 2, 3, 4, 5, 6. There's 6 factorial ways of moving things around. Okay? And then, but within every single, like within this, I can shift this one over to that side, this one over to that side, right? I can move things around in there too, as long as they're next to each other. And so that's where the 3 factorial comes in, because you can do that every time, okay? So that's what's happening here. I'm not going to do all 4,320. I'm not that good. We'll be here for a very long time. But that's the idea behind this, okay? Let's do another one. Let's see if you can catch the pattern here. The artist looks at the paintings again, and she has a group of 3 that need to stay together, and another group of 4 that also you would like to keep together. How many arrangements are possible? Okay, so let's do the 8 here. 1, 2, 3, 4, 5, 6, 7, 8. There's 8 paintings. Now we're going to imagine that the 3 that need to stay together, we're going to put them up front here. They must stay together. So within that bag, you can make some changes, and the answer would be 3 factorial changes you can make inside there. Okay. And then now to to add to this madness, there's another 4 you'd like to keep together. Let's assume they're right here. You'd like to keep those 4 together. So within that bag, you can have 4 factorial iterations, permutations in there. Now let's zoom out. This is one big block, right? This is one big block and another one. So if I were to zoom out, how many different permutations can I do zooming out? 1, 2, 3. 3 factorial ways that you can make changes as long as you keep those bags together. So what would my answer be? In any order you would like, but you got to make sure there's a 3 factorial here, multiplying the 4 factorial. That's my second group. Oh, I'm not going to use groups. Take that off. Together, they're stuck together. And then 3 factorial is like the outside zooming out. Okay, so this is how you would solve a question like this. 3 factorial is 6. 4 factorial is 24. 3 factorial is 6 as well. That's where your study sheet is going to make it a lot faster if you have it. Okay, so what's 6 times 6 is 36 times 24. That's 864 arrangements. Okay, so the more you restrict the scenario, the fewer options you have, guys, right? Because you just can't make as many changes. Like, they need to stay together. So you can't just put, oh, I'm going to take this one, put it out here. You can't do that because it needs to be stuck to all of these ones. So in fact, right, you could swap these two big bags. You could swap them, and then do one where this single painting comes in between them, right? That could be another iteration, another permutation, but you're limited as to what you can do when you zoom out. Okay. This formula I will leave. I'm not going to give you that formula. Don't put it on your study sheet right now. This is what the formula would be if this is a really big, like, let's say you have like 100 objects and you're making groups of like 30, 40, and 50, like it gets really crazy. I've never seen that. So for now, I'm not going to give you a formula because it throws students off. And you can tell, right? It's pretty ugly. So we're just going to leave it for now. Some students ask for a formula, so I just made one up, but I'm not going to give you a formula just yet. So I want you to try this notion that we've discussed on this page right now. And there are some questions that you might wonder, I wonder how to do this. I want you to still give it a try, okay? So see what you come up with. This has to do with keeping things together. See if you can do it, okay? Take a few minutes. There's lots of room, so don't be shy and be like, oh, I don't want answers. But we need to make sure we have our notes filled in, have a few examples that are correctly done. So when there are no restrictions, you just have 13 animals, right? We don't care where they are. They can be all alternating, what have you. So that would just be 13 factorial, right? Some of you actually drew out 13 lines. There's nothing wrong with it. What do we get there? Should have had this ready to go, right? Hold on. You know what? I'm just going to do it live on location because I can't find it. 13. So that's 6227020 Okay, arrangements. This, by the way, listen up to this, guys. This is, in a sense, within our context, that's the universal. Okay? That is our universal set. That's like no restrictions whatsoever. We consider all 13, that's what you get. Okay? If you did the lines, filling in the lines, no problem. Some of you went 13, pick 13. It's also okay to do it that way. So now, all dogs are kept together. This is where I think it's better to shift over to fundamental counting principle, right? So 5, 1, 2, 3, 4, 5, 1, 2, 3. So I've got 13, and I'm just considering eight dogs, right? So within this block, I can make changes. So let's assume for now we're not moving anybody else. We're just moving the 8 dogs in here. So that's where you get your 8 factorial from. Then you zoom out, and I do the zooming out like this, where I count, right? I count this as 1, right? 2, 3, 4, 5, 6. Right? So you've got 6 there. How about we do this? 6, 5, 4, 3, 2, 1. So it's the 6 factorial shows up there. Okay? So your answer is 8 factorial ways within it, but then you can also make changes by moving them around and have the cats all over the place. Okay? So that's 8 factorial times 6 factorial. I'll leave the answer for now, because this is if you get to this part, the rest is just punching it in. I can't find the key right now. I think I made some changes. All cats are kept together. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Make sure you have the right number of. So now the cats are together. So let's assume the cats start off on the left side, and there are 5 of them, so it's 5 factorial. Then you zoom out, and you count this as 1. Okay, 1, 2, 3, 4, 5, 6, 7, 8, 9. That's where the 9 factorial comes in. So that's 5 factorial times 9 factorial. We'll figure out the answer later or never. One of the two. Dogs sit together and cats sit together. So now you've got 2 groups. Okay, so you've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 13. So let's say the dogs are together. 8, I'm counting 8. So you can make changes in there as long as they are together. And the 5 cats, they have to stay together. So you can make changes within there. Every time you move someone, it's a different arrangement. And then you zoom out. How many tiles or how many empty blanks do you have? 1, 2, literally the only thing you can do is, this is one picture, you move them, right? You put all the cats here, all the dogs over there. That's it. So you only have 2 ways to make changes when you zoom out. Okay, so this is where it gets 8 factorial, 5 factorial, and I always like to do the zooming out at the end. Okay, like how many do I have if I zoom out? And so that's where you get that number from. Okay. Dogs sit together, and Manfred and Belinda, they're both cats, they sit beside each other as well. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So dogs again, 2, 4, 6, 8. That's my 8 factorial. Manfred and Belinda, they're right here. You can go Manfred and Belinda, right? Actually, it's MB, Manitoba, right? Because you could do either or, but that's 2 factorial. And then if I zoom out, I have 1, 2, 3, 4, 5. Okay, so this is 8 factorial, 2 factorial, 5 factorial. Will these have the same answer? Yes, it's the same 3 numbers multiplying. So yeah, you happen to get the same answer. Okay? Manfred and Belinda do not sit together. Not. Do you remember? Not be. Set theory. Not be. What would you go? You would go not together. I will go universal minus them sitting together. take away them sitting together from the universal, and that's how you get that. So whenever it's not together, focus on this concept. This is indirect reasoning. So what's the universal? That's 13 factorial minus, where are they together? Oh, I'm a little too fast here. You need to figure out the instance where only those two are together. In this case right here, we also consider that the dogs are all together, correct? So I will just do this on the side here. No, it's not going to be enough room. I will do it actually down here. Them together. Let's do that down here. So we've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So you just want them together. We're going to consider that. So that'd be 2 factorial. Zoom out. Count that as 1. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 12 factorial on the outside. So how would we calculate them being together? 2 factorial times 12 factorial. That'll be the answer. So what are we going to do? We're going to go 13 factorial minus 2 factorial times 12 factorial. I was doing well, Mr. Dirksen, and now you messed it all up, right? I know. Let's do this on our calculator. Okay. So I already have 13 factorial. 2 factorial is just 2, right? So it's going to be 2 times 12 factorial. That's that. So I'm just going to subtract them. Copy, paste, copy, paste. It's a big number. 5, 2, 6, 9, 0, 1, 7, 6, 0, 0. It's like 5 billion in something ways. I'm going to highlight this, okay? Because you might wonder, what's the question? Is that a question? Because you're wondering? Okay. I know I rushed this a little bit. I'm going to bring this back a couple of times, this concept of not, okay? So how would you answer this one? Figure out how many ways dogs are not sitting together at all. No dogs are ever together. You would do universal minus, we already have the answer of dogs sitting together, right? That was B. You subtract this answer from the total, you get that answer, right? So keep that in mind. Okay. I need to cover one more thing before you go on your half weekend. I don't know what you call the Wednesday off. We're going to go to page 24.